Okay. Hello everyone. Welcome to the seventh interaction session of Fundamentals of Electrical Engineering. I'm your TA Dipanita. So today we'll be solving a few problems on the transient and transient analysis of the inductor and the capacitor, which you have been taught in this lecture. So before starting off, few of the things that we will mostly be using in this particular tutorial is that like the transient analysis of the voltage and current of various inductors and capacitors. So let me just write down the equation. um, I don't know if is anyone coming in. Yeah. So if a certain voltage supply is suddenly connected, like a DC supply is suddenly connected across a capacitor, then the voltage across a capacitor cannot change. We have learned this in the previous lectures, right? So slowly there will be gradual change in the voltage, and that is given by, suppose at any time t, which is much greater than just after switching. So it will be voltage at time infinity. Infinity means at the when steady state has been achieved, then what will be the voltage across the capacitor? That plus v of at time equal to 0. So just before switching, what is the voltage? That will be same as the voltage just after switching. So that is given by v0 minus v of infinity, this e to the power minus t by tau, and this tau is the time constant. Okay, so it's not just a capacitor connected in a circuit, there will be other resistor connected in the circuit. So this tau will be equal to r equivalent into c. So this r equivalent is actually the Thevenin's equivalent resistance as seen from the terminal across this particular capacitor. Now, similarly, whenever there is a current source connected suddenly across an inductor, the same, and you should note that this is the steady state part and this is the transient part.
Transport.
Yeah. Anyone wants to say anything? Okay. Good evening. Let's look into. So, if there is a current source suddenly connected to this particular inductor, so the current across an inductor cannot suddenly change, and the response of time particular t will be given by, sorry, the volt, in this case it will be current. So the current is given by, at any time t is given by the current that the inductor will get at infinity. At infinity, this inductor will behave as a short circuit, right? So the current that will be flowing through that inductor at time equal to infinity plus current through the inductor just before switching. Just before switching, this I0 will be I of 0 minus I of 0 plus. Just before and after switching, since inductor resists the change of current, minus I at infinity e to the power minus t by tau. Now, in case of inductor, tau is equal to L by R equivalent. L is the inductance across inductor value as we are seeing, and R equivalent is the Thevenin's equivalent resistance as seen from this particular terminal. So these two, this equation and this equation will be mostly used in all the problems that we'll be solving today. Okay, so let's look at the first problem. Um, it is given in this particular circuit, S2 has been closed for a very long time. That means it has reached steady state. Now this v0 and v infinity, whichever I have mentioned, it totally depends on the switching. When we close the switch when it has reached a steady state in the circuit itself. So in this case, S2 has been closed for a very long time. So S2 is this particular switch. At time t equal to 0, S1 is closed. So just check, like from time minus infinity to 0. When time is between these two, that is to say t is less than 0, greater than infinity, minus infinity. Okay, only this particular switch has been closed, this was open. So the circuit was just this, since the rest of the part of the circuit was open, so nothing was flowing across here. This 1.5 Henry inductor was getting charged from this 4.5 volt source only, and there is a resistance connected 1.5 ohm. So between this time interval, what would have been the current at the steady state? Here steady state will reach just before the switching for this particular moment, minus infinity to 0. So what will be I at steady state? What will happen? This inductor will behave as a short circuit. So basically the circuit will be just as if there is only one resistance. So the current that will be flowing in this particular branch through this inductor would have been 4.5 by 1.5, that is 3 ampere. Now just consider at time t equal to 0 when S1 is closed. When S1 is closed, this 5 volt voltage supply also comes into picture, right? So this has come into picture, this is already there. So 4.5, 1.5 ohm, and this is 2 ohm, this is 5 volt, 1.5 Henry. Now initially, just at when this switch has just been closed, 3 ampere current was already flowing through this inductor because of the steady state that was achieved in this circuit before time t equal to 0. Now we know current across an inductor cannot change instantaneously, so this 3 ampere current should ideally be flowing through the inductor. What you have been asked is to see the change of current through the inductor at time t equal to 0 just after switching. So what do you have to find out? dt of I, right? You have to find this one out. So for that, let us just assume a node voltage V here. Let this be VL. That is, this is at ground, so this is the voltage across the inductor. So just apply node like KCL at A. So what will it be? Let us assume that current I1 is flowing through here, I2 is flowing through here, and this is the 3 ampere current that was already flowing in the circuit. Now when the switch is closed, let us just assume this current. So I1 plus I2 plus 3 will be equal to 0. So it will be VL minus 5 by 2. I2 is VL minus 4.5 by 1.5 plus 3 equal to 0. Someone must be in. I'll just let him in. Yeah. So now you have to just solve for VL, right? So just like VL by 2 minus 2.5 is equal to VL, sorry, this is VL by 1.5 minus 3 plus 3 equal to 0. So this will be equal to um, 1 half plus 1 by 1.5. VL is equal to 2.5. Just take it that side, this will be cancelled. So if you just calculate this, so 0.5 plus 1 divided by 1.5, this comes out to be 1.667 VL equal to 2.5. Now current like voltage across the inductor is given by VL is equal to, how is it related to the current of an inductor? Can anyone respond? If VL be the voltage across an inductor, suppose there is an inductor L and this is VL, and suppose I current is flowing through it, I of t, what will be the relation between VL and I? Can anyone unmute and say?
L di dt.
Right. So L di by dt. So L here is 1.5 Henry. So if we just replace VL, it will be VL equal to 2.5 divided by 1.667. So VL we are just replacing by L di by dt, and L is 1.5. So if we just write it, this will be equal to di by dt is equal to 2.5 by 1.5 into 1.667. So let us just calculate that. Um, Divided by zero point 0.5. So it is, so how much did you get as di by dt? 0.5 1 divided by 1.5. Sorry, this is 1.1677. So now if you do it, 2.5 divided by 1.5 divided by 1.1667. So it comes out to be 1.428 ampere. 1.428 ampere per second. So this is equal to, as given in option D. Everyone is following the solution?
Yes.
Okay. Then we'll
Yes,
proceed
ma'am.
with next question. So for the next question, what you have is in this figure, the switch S1 is closed at t equal to 0 and S2 is opened at t equal to 4 millisecond, assuming the inductor is initially relaxed. Assuming the inductor is initially relaxed means no current was flowing through the inductor, that is I of 0 at, this is the time when time is equal to minus infinity. Okay, so this current is equal to 0. Okay, determine the current through the inductor at t equal to 5 milliseconds. So for that we need to know the initial state of the inductor. So let us divide this problem into two sections. When one is when S1 is just close at t equal to 0. So one is from t equal to 0 to 4 milliseconds, just before S2 has been closed, just up to that, before that. So in this particular like time, let us draw the circuit. S1 is closed, so this switch has just been closed, and before that it was given that inductor is relaxed, that is in this case I of 0 is equal to 0. Now when S1 is closed, and in the, as per given in this problem statement, S2 is open, that means S2 has been closed from start itself. So initially the circuit was something like this. So this is closed. This is 50. This is 0.1. This is 100. Okay. So at time t equal to minus infinity, this was closed. No current was flowing. It was all fine. Now at time t equal to 0, this switch has been closed. But this is a kind of a short circuit, right? So it will bypass this 100 ohm resistance, and current will simply flow like this, right? This is 100 volt. Now for this particular time range, the equation at I of t, that is equal to I of infinity plus I of 0 minus I of infinity times e to the power minus t by tau, right? Now what will be at I equal to infinity within this range, that is 0 to 4. Let us assume at 4 it has reached steady state. So what will happen at 4 millisecond is this inductor will behave as a short circuit within this time
Yes.
frame if we assume the steady state. So what it will see is only a 50 ohm resistance, right? So the current that will be
Yes.
flowing here at time t equal to infinity will be 100.
1.
Yes, 100 by 50, 2 ampere, right? So it will be 2 plus 0 minus 2 e to the power minus t by tau. Now what is tau? Tau is equal to L by R equivalent, right? So L here is 0.1. R equivalent, it is just 50 ohm because there is no other resistance. It is seen across this particular voltage. So it will be 50. So if we write it properly, it is 1 by 500, right? So just write it 2 minus 2 e to the power, this will be 500, 1 by 500. So e to the power minus 500 t. This was the state equation just before S2 is opened. Now whatever the final state at t equal to 4 second will be, this will actually be the starting like current of when at t equal to 4 millisecond this switching is happening. So let us calculate what the current is through the inductor at time t equal to 4 millisecond. So it is 2 minus 2 e to the power minus 500 into 4. Since it is millisecond, t is in second, we have to write t to the power minus 3. So this I4 will be equal to, let us just calculate it, 2 minus 2 e raised to the power. So 504 20. So it is 2 e to the power minus 2. So where is it? It will be 1.729 ampere. Now at 4 millisecond what is happening is S2 is opened. So now the circuit kind of looks like this. So one resistance here, another resistance here. Since this is open, the inductance is here. So what happens now is that the time constant tau, that value will change because now it is seeing two resistance, 150 ohm, 100 ohm. And initially this 1.729 ampere current was flowing at t equal to 4 millisecond. Now at this t equal to 4 millisecond switching, that is here now I0 is actually like I0 is actually I at t equal to 4 minus, so it is 1.729. Now the time constant of this new after switching this circuit will be L is still 0.1, R equivalent is 100 plus 50, so it is 150. So 1 by 1500. Let me use a different color pen. Now for this let us write the equation. So let us also calculate I infinity first. So at time t equal to infinity, what will happen? Inductor will behave as a short circuit and it will just phase these two resistance. So current at infinity will be, voltage is still 100 volt, so 100 by 150, that is 2 by 3. So the new equation I of t after switching after 4 millisecond, that is t greater than 4 millisecond, it will be I of 0 here is 1.729.
One,
Sorry, I infinity it should be, right?
2/3.
Huh. It should be 2 by 3. 2 by 3 plus 1.729 minus 2 by 3 e, e to the power, sorry, minus t by 1 by 5 1500. So what you have been asked is to find that, like find the inductor current and time equal to 5 millisecond. So in place of this t, you just put 5 millisecond and you will arrive at the answer. So can you quickly, just calculate this and tell me which is the correct option? You have the equation now. It's just a straightforward calculation. So did you guys get the correct option? Please note that t is equal to 5 milliseconds. So it will be 5 into 10 to the power minus 3. Right? 0.66 plus 1.729 minus. So how much are you getting? Okay. So there is some. I have missed something in this particular equation. Can you tell me? Can anyone point out? See, for this particular case, what we have done is like this I of t, writing it as I of t is actually not the correct, thing, right? Because we have assumed like we are starting from 4 milliseconds. So uh, I think sir has, if you remember, sir has taught in his lecture about like when you apply a DC pulse. So like suppose from 0 to 4 second, then you apply another DC pulse from 6 to whatever second. So it, this time shift here now we have to consider in this particular equation, right? So just see, I will write here. So now when we have like assumed that we are considering from t equal to 4 millisecond, this particular thing should be incorporated in the time that is in the transient, response also, right? So it will be, this particular equation will be t minus 4, right? 4 millisecond. It should be like this, right? Instead of t it will be t minus 4. So I'll just, so the equation now, since we are starting from 4 millisecond, it will be instead of t, it will be t minus 4 because 4 millisecond has already passed. So here at t equal to, like, the 0 point starts from 4 millisecond, right? Do you agree or not?
Yes.
Okay. So since it is in millisecond, we have to write 10 to the power minus 3 by the time constant, which is 1 by 1500, right? So it will be 0.66 plus 1.729 minus 0.66. So this is 1.069 e raised to the power minus. Now we have to find at I equal to 5 millisecond, right? So if we put t equal to 5 millisecond, 5 minus 4, that is 1 millisecond. 1 into 10 to the power minus 3. And if you take 1500 up, it is 1500. So it is 0.66 plus 1.069 e raised to the power um, 1.5. So it comes out to be 0.9, which is option C, 0.905. Everyone clear on why we took like t minus 4 into 10 to the power 3 minus 3? If you have any question, you can ask now. Otherwise, we'll move to the next question. No? Because we'll be
No, ma'am.
solving a similar kind of problem later also. So that time, I will ask you. So everyone clear on this one? We can move to the next one then?
Yes, ma'am.
Okay. So now, for the third question, um, in this particular circuit, this particular switch is opened at t equal to 0. We have to find the current in this inductor at t equal to just greater than 0. That is at time t equal to greater than 0. So can you tell me how will we like start solving this problem? First, what do we have to find? See, to
First, we need
find,
to consider steady.
yeah,
First, we need to consider steady state condition that switch is closed for a long time, right? So it
right,
has reached its steady state.
right. So the switch is closed for a long time. So the circuit was, well, it is just open and the t equal to 0. Okay. So the switch was closed. So the circuit is now somewhat like this, right? And there is one inductor here. Now, since the circuit has been closed for a very long time, inductor will act as a short
Okay.
circuit. So, see, check, this is like node A, and this is a super node kind of a thing. So this is node B. So this 32 ohm resistance, both of them are parallel with each other, and there is a short circuit across it. So they won't come into picture at all. So during steady state, what will happen is we will have only this 6 ohm resistance, this 8 ohm resistance, and this 8 ohm resistance. Since there is a short circuit, that too will not affect. And this is the current that is flowing through the inductor then. So this is 30 volt. So the total current that is flowing, let us say it is I dash will be equal to 30 by the equivalent resistance. Now this 8 ohm and 8 ohm are in parallel with each other, right? So the equivalent resistance will be 6 plus 8 parallel to 8. 6 plus
10.
64 by, um, yeah, it is 10. So the current that is flowing like before time t equal to 0 is like the I dash.
3 amperes.
Yeah, it's 3 amps. Now what do we have to find is the current that was flowing through the inductor, which is equal to I. So if you just apply current division rule, it is so at this particular node here, here 3 amps is entering, and it will get distributed in this two branch. So since both the resistance are equal, so it is 8 by 8 plus 8 16 times 3. This is by current division rule, right?
1.5.
Yeah,
Yes.
1.5 ampere was initially flowing through it. So I of 0 is 1.5. This, sorry, for this case, like this is infinity. Now when we during the switching condition, that is I of 0 minus, which is actually the stated state combination before switching. So this is 1.5, and this will be equal to the current just after switching. So now I of t is I infinity plus I of 0 minus I of infinity e to the power minus t by tau. Now let us consider when switching has already occurred. That is, this switch has been opened and only this part of the circuit are connected. So now the inductor is connected to the combination of resistance 8. So just imagine, like in this condition, when this circuit will reach a steady state, if this inductor is acting as a short circuit, there is no supply, no external supply of voltage, and if inductor is acting as a short circuit, there is no other sources, the current through this inductor will gradually die down and reach 0, right? So for this case, this infinity is like this infinity, I infinity is both 0. So it is basically I of 0 e to the power minus t by tau, and I of 0 we already have 1.5, right? Now tau you have to find out. Tau is the equivalent resistance as seen from this inductor, right? So it is this 32 ohm resistance is in parallel with 32 ohm resistance is in parallel with a combination of 8 plus 8 ohm resistance. So 1 by R equivalent will be equal to 1 by 8 plus 8 16 plus 1 by 32 plus 1 by 32. So if you just calculate this, 1 plus half. So 1 2. So 2 by 16, that is 1 by 8. So R equivalent is equal to 1 by 8. Sorry, R equivalent is equal to 8. So and tau is equal to L by R equivalent, right? L is 2 Henry and R equivalent is 8. So it is 1 by 4. So this is equal to 1.5 into 1 by 4. So 1.5 e to the power minus 4t, which is option A. Everyone got it? Everyone got this? Any
Yes, sir.
problem here?
Yes, ma'am.
मैम आर इक्विवेलेंट कैसे निकला?
Okay, R equivalent. So, see, this, I'll take just a different color. So now when this switch has been opened, this entire circuit will be this much, right? So this is an 8 ohm resistance, another 8 ohm resistance. This is a 32 ohm resistance. there is another 32 ohm resistance, and
Okay, okay, ma'am.
the
Understood, ma'am.
inductor is connected here, right? So now you
Okay,
got it.
understood, ma'am. Yes, ma'am.
This 8 plus 8 16 here, parallel with 32, parallel with 32. So this is three resistance in parallel with each other. Okay. So can we move to the next question?
Yes, ma'am.
Okay. So here, one particular circuit is given, and it is said that um, a, this current waveform is applied, like the current similar to this waveform I was given here is applied. This current pulse is applied, and we have to find v of t at t greater than 1 second, assuming v of 0 is equal to 0. That is initially the steady state of the circuit. There was no voltage stored in this particular capacitor. So at time, so here we see, like between time 0 to 1 second, 1 2 ampere pulse was given to this circuit, and then it is again 0. So if we just since for a capacitor we need to write it in terms of voltage, let us just convert the circuit by using source conversion. A resistance in parallel with a current source can be replaced by a resistance with a voltage in series, right? And this voltage will be equal to I into R, that is Is into R is 2 ohm, that is 2 Is, right? And this 4 ohm resistance is there. This is the capacitor that is already connected. So this is the voltage, this is the 2 ohm resistance, this is the 4 ohm resistance. Now just let us consider like between the time 0 to 1 second, like just before this pulse goes off, let us consider that particular time. In that particular time, what will be the v of t? That is v of infinity plus v of 0 minus v of infinity e to the power minus t by tau, right? So v of 0 is given as 0 in the question itself. It is given v of 0 is equal to 0. Now what we have to find is v of infinity. So whenever there is like at steady state, capacitor will act as a open circuit, right?
Okay.
So
Yes.
in steady state there will be no current actually flowing through the circuit, because this will behave as a open circuit. So it will be like this. Sorry, we there is a source here, of course. So this 2 ohm source, and this is vs. So between 0 and 1, what will be equal to is? Vs is equal to
Zero.
is into 2, right? Is is,
Zero.
yes, 2 ampere. It is given in the question. So it is Vs is will be equal to 4 volt, 2 into the resistance 2. So this entire voltage will appear across this Vc, the capacitor voltage, since at steady state it will, like at time just before switching, like between this time interval 0 to 1, it will be V equal to 4 volt, right? So 4 plus 0 minus 4 e to the power minus t by, now tau. What is tau? Tau equal to RC. C is given as 0.5 farad. And what is R equivalent? R, this 4 and 2 are in series with each other, right? So 4 plus 2, 6. So this is tau
Correct.
is equal to 3. So it is 4 into 1 minus e to the power t by tau is 3, right? This is at time, this is between this time interval 0 to 1. So to calculate what happens for t greater than 1, we need to find what was the condition at t equal to 1. So v of t 1 will be 4 1 minus e to the power minus 1 by 3. So let us just calculate this. 4 into 1 minus 8 to the power minus 1 by 3. So it is v at time t equal to 1 will be 1.1338. Okay. Now consider at time t equal to just greater than 1. So voltage across a capacitor cannot change instantaneously. So at t equal to 1 minus will be equal to v t equal to 1 plus will be equal to v at 1, which is 1.1338 volt. Now at t greater than 1, what will be the steady state equation? There is no voltage now, so this capacitor will gradually die down, and this like the charge will be like it will be discharged and it will get exhausted. So at t equal to infinity, this entire capacitor will get exhausted, right? The charge will get dissipated, discharged. So the voltage at infinity for this circuit, when there is no current pulse here, will be equal to 0. So the vt the vt new equation will be v equal to infinity, which is 0, plus it is 1.1338 minus this will be 0, right? Now what will be e to the power? So
minus 1.
right, t minus 1 by tau. The tau remains the same, right? Because both the resistance are there. So it is 2 plus 4 6 into 0.5 RC. But note that t minus 1 will be there. So it is 1.1338 e to the power minus t minus 1 by 3, which is given in option D. This is the correct option. Okay. So we will move to the next question. If anyone has any doubt, you can ask. Otherwise, we'll move to the next question. Okay. So in this particular question, what is given? There is a circuit, and it has been, this particular switch has been open for a long time. If it is closed at t equal to 0, then what is the magnitude of current through this particular 4 kilo ohm resistance, right? So yeah, so let us find the circuit like before time t equal to 0 and after t equal to 0. So before t equal to 0, this switch is open, right? So the circuit is, this is the capacitor. We will draw it later. Let us draw the voltage source first. 30 volt. Okay, this is okay. So switch has been open for a very long time. This very long time signifies the steady state has been achieved, right? So what will happen is the inductor will act as a short circuit. This will act as a open circuit, and there will be a voltage, that is, which appears when charge are getting stored in this capacitor. So first we have to find what is this VC, right? So we have 10 kilo ohm, 4 kilo ohm and 1 kilo ohm, and this is the current that is flowing at steady state. So let us simply solve the circuit. So let us first calculate what is IL. IL will be equal to 30 by 10 plus 4 plus 1.
15. 2.
So it is 30 by 15
2.
is 2 ampere.
2
So
million.
2 ampere current is flowing through the
Million.
inductor. Now what will be VC? Just apply current division rule, like the total voltage is 30. So it will be the voltage across this 4 ohm and 1 ohm resistance, right? So the total resistance is
Like
5.
that.
Yeah,
Actually, resistance is in kilo ohm, na ma'am. How IL
right,
can
right. This
across
will be
2 amp.
right. This will be in milliampere.
That's
Yeah. Since this is in kilo ohm, that means this is 10 to the power minus 3. You're right. It will be in milliampere. Now voltage, so here in this case it doesn't matter because there will be kilo ohm here and kilo ohm here. It will get cancelled. So voltage is 10 volt. So 10 volt is 10 volt is getting like it is the voltage drop across these two resistors, which is also is equal to VC, right? So when the switching has been done, that is this switch is closed, just look at the circuit, like this initially just before switching this capacitor was acting as an open circuit, the inductor was a short circuit. Now as soon as this switching has been done, so the current, like what will happen is, like initially this voltage change across this capacitor will be resisted, and the current change across this inductor will be resisted, right? Since it is given t equal to 0 plus, that is just after switching, it is not talking about t equal to greater than 0. This means like just like a lot greater and what happens beyond. But at t equal to, just at t equal to 0 plus, we have to find what is the current through this 4 ohm resistance. So what will it be? Let us just draw the circuit. Now there is, because of because this switch has been closed, the circuit is like this. So this is 30 volt, and so this is the inductor, this is the capacitor, and this is 10 volt, and the current that was flowing through here was 2 milliamps, right? Now if like if we apply so just when the switch has just been closed, so what will be the new current that is flowing through this particular 4 kilo ohm resistor? 10, and this is 1. So this, because there is a short circuit here, this 2 ampere current which is initially flowing through here, that will get disrupted, right? Now this 10 ampere 10 voltage is also getting applied across this particular resistance, right? And there is a short circuit here, that is because of this switch closing, the short circuit is here, so it will not take into account this particular 1 kilo ohm resistance. So it will be like a current that is getting flown like this. So because at t equal to just 0 plus, this capacitor will try not to change the voltage. So there is this 10 voltage across this 4 kilo ohm resistance. So the new current that will be flowing just at t equal to 0 plus will be, the voltage will be sorry, the current will be, voltage across this is 10, because if we consider this particular loop, it is just 10 volt that is getting applied, and the total resistance in this loop, that is 4 kilo ohm, which is 2.5 milliampere. So you have to find the magnitude of current in milliampere. So the correct option is option B, 2.5 milliampere. Everyone got this one?
Yes.
Okay. So this is pretty much what we have to do for today. In case if you have any doubts or clarification, or if you have any specific question to ask, you can ask. Otherwise, we can like get it over for today. So like in this steady state analysis, these is like the major thing that you have to look into is this two equation. Pretty much governs the entire circuit. But what you have to make sure is how you define your conditions. Like I equal to 0 and I equal to infinity will depend on how you are giving the switching condition. Depending on that, just calculate it and you will always like do it right. So do you have anything else to ask? Otherwise we can stop the session for today. Okay. uh, Thank you for coming.